Hello everyone. In today's lecture we are going to study about relative stability. So, how system is stable? How stable it is? If a system will remain there for a long time, or will a certain change in parameter push it to the verge of instability? Certain change in gain will push it to the verge of instability. So I want a reasonably good measure of how stable my system is. So what we know after we say that, well, the first requirement is the system should be stable. Next is to ensure that the adequate relatively stable. Now how does we measure relative stability? Okay, so look at these two things, this orange one and this blue one. So this is the set of poles here, open loop poles, and there also a set of poles here, right? One is here, another is here, right? So now I go, so this is my S plane, psi and j omega. So these are the poles. Let's say the system just has two poles, this one, and I plot a Nyquist for this orange one over here. Okay, so and this blue guy goes here, so this blue guy Nyquist plot is here. So now here I look at the stability in terms of distance from the imaginary axis, right? So if I am closer here, get closer until here, there would be a point where I just tip off the right side here. Even if I am just very slightly to the right, I am still unstable. Even if I lose by 1 run in a cricket match or 100 run, I still lose, right? So it is the same thing here. So how does Nyquist thing now look like here? I just can't directly measure relative stability. I can say, well, they are further from zero origin. So it will take, it will still be safe if there are some change in parameter or things like that. It will still be safe if there is some change in parameters or things like that. So it may just come slightly to the right, or maybe even more to the left, and so on. Okay, but I can say that this look little more hopeful, this blue one, than this orange one. Okay, so this pair is more hopeful. Now let's come back here, right? So here, what is the point of interest? So as long as P is equals to 0, my open loop system is stable, and I just want Z is equals to 0. If Z is equals to 0, Nyquist tells me that my system is stable. Now who decide this? So this is my guard. Right? Who says, well, you cross this line. In this, if you cross this line or trespass, you become unstable. So the idea would be key. Well, I just say, as far as from this line, this number -1 plus j 0, right? So look at this blue one. It starts here. Brownish also starts here, but it's still closer. This one is more closer than this blue one to this point -1 plus j 0, and I want to stay away from this point -1 j 0. Say something change, and then if it would just, if you will just draw it, like if some change in makes it more than -1 plus j 0, so it will keep encircling. I just didn't draw it properly, but The thing is, if I encircle minus 1 plus j 0, right? So I will become unstable. Because I am actually encircling the point minus 1 plus j 0, I didn't really draw a smart picture here, but something like this. So I want you could see this one. If something keeps changing, you may just stick to over here. Okay, and then what happened when I am here on the pole, my pole are on imaginary axis. So if I draw the Nyquist here, if my poles are at imaginary axis, it will be like this. Nyquist will be plot like this on horizontal line, and this depends on omega increasing or omega decreasing, right? So based on this, I can quantify something as a measure of relative stability. Again, the idea is to stay as far as from minus 1 plus j 0 or further to the left. Of course, you can't really say that I will have a pole at plus minus 1 million plus minus j whatever, something like j 10,000. This is also not practical, feasible, right? So we have to make sure some reasonable assumption here, or so get some reasonable estimation of this thing. Okay. Now, what is the beauty of Nyquist plot? So Nyquist plot indicate not only whether the system is stable, but also the degree of stability. So we also see how it will give information if the system is stable. System stability can be improved, right? And then since the decision factor is this guy minus 1 plus j 0, so what does the plot tells us? Either polar or Nyquist, that as the plot get closer and closer to minus 1 plus j 0, the system is on the verge of instability. Okay, so closer it is to the minus 1 plus j 0, larger is also the maximum overshoot in the step response. Is the settling time, closer I am to the minus 1 plus j 0, which means closer I am to the origin here, and which means damping is small, and things like that. Now, okay. Now, so let's do it little graphically. So let's say this is I'm not interested really in in the Nyquist in the exact is the in the exact transfer function, but say something look like this, right? So this is Nyquist plot, this guy, or even the polar plot, and this is the point minus 1 j 0, and I just draw a circle around here. Say the distance here is minus 1, and distance till here is a. So what is this distance? So this distance is when imaginary part goes to 0. So let us say imaginary part of g j omega h j omega at omega equals to omega 2 is equals to 0. Or in another word, you can even say that the angle would be angle is minus 180 degree. So this is the thing here, right? This is omega 2. So what would happen that if A is getting closer and closer here, so I can I am on the verge of instability. Say I have something like this here. Say I have like this and something like this, right? So I increase the gain and I go here, and say I have actually encircle this point. So I will just do some detour like this, and I can say that the system is going to the verge of instability here. So this is not important. So there is something which this can tell us the distance, how far this guy is from this point. Not only, now look at this circle also. See, well, it intersects this guy here, right, at frequency omega 1. So over there, its magnitude of g j omega h j omega at omega equals to omega 1 is 1. Now keeping this constant, okay, if I'm keeping this constant, this magnitude constant, and moving here on that side along this, means I'm adding some kind of angle to the system, and I'm just moving here till here, right? So if I add some angle phi in this direction, then I hit minus j plus j0. So I hit the point when, well, then I am on the verge of instability. So there are two things: the distance, how far this is from this point, and second also how far the angle is from minus 180 degree. So these two will quantify this A and phi. A and phi will quantify, will give us some measure of relative stability. So far I just said that just be further from the origin in the S plane, then I would talk in terms of pole. They are on imaginary axis. The system is just marginally stable. Slightly to the left, it is unstable. Okay, so here it is on verge of instability, right? So now I can actually quantify these things. If my magnitude is keeping increasing, and once it's become equals to this minus 1, then also my system will become unstable. And similarly, if this angle keeps on increasing and it will become minus 180 degree, then also my system will become unstable. So let us say these things little more formally now. So the Nyquist cross imaginary axis at frequency omega equals to omega 2 with an intercept of, right, omega 2, and this intercept is called A. And then unit circle intersect locus g j omega h j omega with the frequency omega equals to omega 1. Okay, so I just draw a unit circle because this point minus 1 plus j0 was my interest point, right? So the phasor of this makes an angle of phi in with negative real axis. Again, the usual measurement is we measure the positively in counterclockwise direction. Okay, so phasor of G and H makes an angle of phi with negative real axis as a measure of positive in counterclockwise direction. So angle phi from here till here, and then, well, this is now kind of known to us, right? We know why this is true, that a locus approaches minus 1 plus j is 0, the relative stability reduces. And this happen in two cases, right? So this happens when the value of a, of this is the a, when the value of a is, because value of a approaches unity and phi approaches 0. So for this angle, if I measure for gj omega equals to minus 180 degree, so a approaches 1 should be bad news for us, and in similar way phi approaching 0 will also be bad news for us. So therefore we use this guy a and phi as a measure of relative stability. So we will use these two quantity a and phi to define the measures. Now we will name each of them, right? So this guy a relates, or we can call it gain margin, and this guy phi is called as phase margin. Name will already tells us what they mean. Okay, so in detail about them we will study in next lecture. That's all for today's lecture. Thank you.